On the morning of October 4th, 2024, something happened on the surface of the Sun that no human instrument had ever captured before. Not in the 70 years we have been watching our star with satellites. Not in the centuries we spent sketching sunspots with telescopes from the ground. What the sensors recorded that morning broke every category scientists had built to describe solar activity. And the worst part, the part that kept researchers staring at their screens long after midnight, was the direction it was pointed. Straight at us. To understand why this matters, you need to understand what the Sun actually is when it is angry. Most people picture the Sun the way you see it through a car window, a bright disk sitting calmly in a blue sky. But that image is like watching the ocean from a plane. From up there it looks flat and still. Get in the water and you realize it is an engine of chaos, constantly churning, constantly throwing things outward. The Sun is the same. It is a ball of plasma the size of 1 million Earths, and its surface is never still for a single second. Every few years the Sun goes through what astronomers call a solar maximum, a period when its magnetic field becomes so tangled and stressed that it starts releasing enormous bursts of energy. We're in one of those periods right now. In fact, we entered the most intense solar maximum in 2 decades, right as the events of late 2024 began to unfold. And that timing matters, because what happened in October of that year was not just one event, it was a sequence of events, stacked on top of each other, each one amplifying the next, building towards something that our models had theorized could happen but had never actually observed. Scientists have a name for this kind of stacking. They call it a perfect solar storm. To understand the scale of what was coming, we need to go back to the largest solar event in recorded history. On the 1st of September, 1859, an astronomer named Richard Carrington was in his private observatory outside London, sketching sunspots as he did most mornings. What he saw next stopped him cold. A brilliant flash of white light erupted from the Sun's surface, so intense and so fast that it lasted less than 5 minutes. He was one of 2 people on Earth who witnessed it directly. Neither understood what they were seeing. Within 17 hours, the effects arrived. Telegraph lines across the United States and Europe burst into sparks. Some operators received shocks through their equipment. Others reported that the telegraph networks continued to function even after they disconnected the power, running entirely off the energy surging in from the sky. The northern lights were visible as far south as Cuba and Hawaii. People in the Rocky Mountains woke up thinking it was dawn, not realizing it was 2 in the morning, and what they were seeing was the Aurora burning overhead. The Carrington event, as it became known, was a 10 on a scale of 10. It hit Earth at a time when our most advanced technology was a wire strung between wooden poles. If the same storm hit today, the estimates are staggering. Transformers across entire continents would fail. GPS satellites would go blind. Aircraft communications would collapse. The power grids in North America and Europe, which are not designed to handle the kind of electrical surge a Carrington-level storm produces, could take months or even years to restore. The economic damage would be measured in the trillions. Now here is what the scientists watching the Sun in October 2024 actually saw. It started with the emergence of a sunspot region so large that amateur astronomers photographing it from their backyards could see it with solar filters. Sunspots are areas where the Sun's magnetic field lines have bunched up and broken through the surface. They look dark because they are slightly cooler than the surrounding plasma, but cooler here is relative. A sunspot is still several thousand degrees. What makes them important is not their temperature, but their magnetic stress. The more tangled the field lines, the more energy can suddenly release at once. This particular region was classified as the most magnetically complex structure solar scientists had observed in over 2 decades. It was not one tight knot of magnetism, but a sprawling, chaotic web of competing field lines that stretched across a surface area larger than 20 Earths. Researchers at monitoring agencies on 3 continents were tracking it in real time, and most of them were not worried about a single large flare. They were worried about something more dangerous, a sympathetic eruption. A sympathetic eruption is when one explosion on the Sun triggers another. The energy wave from the first event travels across the solar surface and disturbs a separate, already stressed region, causing it to explode in turn. Researchers had documented sympathetic eruptions before, but always between nearby regions. What the data in October 2024 began to suggest was that the eruptions were occurring between regions on opposite sides of the Sun, interacting through pathways deep inside the solar interior that the models had not fully mapped. Then came the third element, and this is the one that changed the conversation from interesting to unprecedented. Hidden on the far side of the Sun, a region that ground-based telescopes cannot directly observe, spacecraft were detecting the signature of something enormous preparing to release. Researchers use a technique called helioseismology to see through the Sun the way doctors use ultrasound to see inside the body. By reading the vibrations moving through the solar interior, they can infer what is happening on the hemisphere facing away from Earth. What the seismic data showed was a magnetic structure of a size and configuration that had no precise historical match. On October 4th, that far side region erupted. The explosion was so energetic that it was visible to spacecraft positioned at different points around the solar system, including probes that monitor the Sun from angles Earth cannot see. The initial burst of light and high-energy radiation reached Earth in about 8 minutes, as light always does. That part was survivable. The X-ray surge caused radio blackouts across the sunlit side of Earth for about an hour. Aircraft operating over the Pacific reported losing high-frequency radio contact. That was the first warning. The second warning arrived in the following hours, as the full scope of what had been launched became clear. When the Sun erupts in a major event, it does not just produce light, it hurls matter. Billions of tons of plasma, magnetized and moving at millions of miles per hour, eject into space. Researchers call this a coronal mass ejection, which is the technical description of the Sun essentially throwing a piece of itself into the solar system. A typical ejection, if aimed at Earth, takes between 1 and 3 days to arrive. The cloud expands as it travels, and when it reaches our planet, it connects with Earth's magnetic field in ways that can be gentle or catastrophic, depending on the orientation of the magnetic field embedded in the cloud. What made October 2024 extraordinary was not just the size of the ejection, though it was enormous. It was the interaction between multiple ejections that had been launched in the preceding days. Over the 72 hours before the main event, the Sun had already launched several large eruptions, each one travelling out through the solar system ahead of the primary cloud. These earlier ejections had modified the space between the Sun and Earth, a region called the interplanetary medium. They had swept it clean of some of the denser solar wind, reduced certain kinds of turbulence, and created what researchers describe as a preconditioning effect. They had, in a sense, cleared a path. When the October 4th ejection launched into that cleared path, it did not slow down at the normal rate. It did not disperse the way typical ejections do. It accelerated and maintained its coherence in a way that surprised researchers studying the tracking data in real time. One analyst at a space weather forecasting center later described it as watching a bowling ball thrown down a lane that had been oiled. It just kept going. By the time the cloud was halfway to Earth, instruments were revising their arrival estimates downward. It was coming faster than the initial models predicted, and it was larger. The magnetic field embedded in its leading edge was oriented in a direction that researchers call southward pointing, which in the language of space weather is approximately equivalent to the worst-case scenario. A southward pointing field connects most efficiently with Earth's magnetic field and allows the maximum possible energy transfer into our magnetosphere. Research teams around the world began issuing alerts. Emergency management agencies in several countries quietly began preparing contingency protocols. Power grid operators in North America and Europe were notified to prepare for possible switching actions to protect transformers. Satellite operators began maneuvering some assets to reduce their cross-sections to the incoming storm, and then, over a period of roughly 18 hours beginning on the morning of October 10th, it arrived. The first thing that happened was the Aurora. People who live in Norway, Iceland, Canada, and Alaska are accustomed to the Northern Lights. What happened in October 2024 was not for them alone. The Aurora appeared across the contiguous United States, as far south as Texas and Florida. It blazed over England, France, Spain, and Portugal. People photographed it from New Zealand and southern Argentina. It was one of the most widespread aurora displays in the modern era, visible to hundreds of millions of people who had never seen anything like it. The colour palette was striking. Green and white are the standard produced by energized oxygen atoms at moderate altitudes. but the storm drove particles deep enough and hard enough into the atmosphere that it also lit up reds, and in some places purples and blues that experienced Aurora watchers said they had never personally witnessed before. Social media filled with photographs within hours. For most people watching, it was simply beautiful. For the engineers and researchers watching different instruments, it was not simply beautiful. The effects on technology were significant, though they fell short of the worst-case scenarios that had kept people up the night before. Several communication satellites experienced anomalies. Some went into protective safe mode automatically, temporarily interrupting service. GPS accuracy degraded across large portions of the northern hemisphere for several hours, with errors of tens of meters affecting navigation systems that rely on precision to the sub-meter level. Agricultural equipment that uses automated GPS guidance, construction machinery with satellite positioning, precision survey instruments, all of them accumulated errors during the disturbance. Power grids in the northern United States and Canada experienced geomagnetically induced currents, the invisible flows of electricity that solar storms push through long stretches of conductive infrastructure. Grid operators made rapid switching decisions to reroute power and protect transformers. There were localized outages, though grid managers largely succeeded in preventing cascades. The system held, but operators described it afterward as one of the most demanding real-time management situations many of them had experienced. Airlines rerouted flights away from high-latitude paths, adding time and fuel cost to hundreds of journeys. High-frequency radio communication used by pilots and maritime operators was disrupted for extended periods. Some remote communities in Arctic regions that depend on high-frequency radio as their primary communication link experienced significant isolation during peak disturbance hours. The total economic cost of the disruptions was later estimated in the hundreds of millions of dollars. That sounds large until you consider what was theoretically possible if the storm had been 30% more powerful, or if the preceding ejections had been oriented differently, or if the preconditioning effect had been more complete and the cloud had arrived even faster. The October 2024 event was a 10 on the modern space weather scale, which researchers used to rate geomagnetic storms. It tied or exceeded readings that had not been seen since a major storm in 2003, which itself was the strongest of that era. But the scientific significance of what happened went beyond the storm intensity rating. What made researchers pause, what sent the papers flooding into journals in the month that followed, was the chain of physical processes that had produced it. The sympathetic eruptions across opposite hemispheres of the Sun, the preconditioning of interplanetary space by preliminary ejections, the speed maintenance of a large cloud through a modified medium. These were not individually new phenomena, but the particular combination, the specific sequence, the scale at which they interacted produced an event that fit no single prior template. Researchers began using a phrase that appears in the scientific literature more often than it used to, an event outside our observational baseline. What that phrase means, stripped of its academic caution, is that we do not have a clear historical precedent for exactly this. We have the Carrington event from 1859, but we have no instrument data from it, only the qualitative reports of telegraph operators and Aurora watchers. We have a cluster of large storms from the mid-20th century that we know occurred, but did not have satellites to measure precisely. We have the detailed satellite era beginning in the early 1970s, and within that era we have a handful of very large events. October 2024 sits near or at the top of the measured list, and here is what that means for the question everyone eventually asks: could it happen again? Not just a repeat of October 2024, but something larger, something comparable to what arrived at Earth in 1859, measured with modern instruments, hitting modern infrastructure. The answer from the research community is not reassuring. The Sun is not a system that can be controlled or predicted with the precision we would need to give confident all clears. Solar cycle 25, which we are currently in, reached its predicted maximum earlier than models forecast and exceeded the intensity projections. The magnetic complexity that drove the October events has not resolved. The sunspot regions that produced the eruptions have rotated around the solar disk, but the underlying conditions that made them so energetic are properties of the entire cycle, not just specific regions. The probability of a Carrington-scale event in any given decade has been estimated by different research groups at somewhere between 10 and 12%. That sounds low until you think about it the way you think about other low-probability events with catastrophic consequences. A 10% chance per decade means that over a 50-year period, the probability of experiencing such an event approaches 50%. Over a century, it exceeds 80%. And the world that would receive a Carrington-scale event today is categorically different from the world of 1859. The telegraph network of that era was essentially a curiosity, a tool of business and journalism. The infrastructure we have built since then is woven through every aspect of modern civilization in ways that have no parallel in history. The power grid, the satellite constellation, the internet, the financial transaction systems, the supply chains, the medical equipment, the water treatment facilities, all of them have dependencies on electricity and on precise timing signals from GPS satellites that simply did not exist when the last great storm arrived. A realistic modelling of a Carrington-level event in the present day produces outcomes that researchers find genuinely difficult to communicate without sounding alarmist. But the numbers are the numbers. Some models project that a worst-case major geomagnetic storm could result in grid damage requiring 12 to 18 months to fully repair in the most affected regions. In those regions, without electricity, the cascade of secondary failures is not difficult to imagine. Refrigeration, water pressure, hospital backup power, communication, food distribution, heating in winter regions, all of it becomes unreliable within days. None of this is speculation. It is the product of serious infrastructure analysis conducted by engineering researchers and government agencies over decades. The gap between what the research says and what the public understands is significant, and it is one of the reasons that space weather scientists have been increasingly vocal in recent years about the importance of improving both our forecasting capabilities and our infrastructure hardening. Here is where there is genuine good news, though it comes with important caveats. The warning time we have between a solar eruption and its arrival at Earth, typically between 1 and 3 days for the mass ejection component, is enough time to take protective action if we use it well. Power grids can be configured to reduce vulnerability. Satellites can be placed in safe mode. Airlines can reroute. Operations that require GPS precision can pause. None of these actions are cheap or simple, but they are possible, and they have been demonstrated to reduce damage significantly. The problem is the gap between the warning we can currently provide and the warning we would need to provide to implement those protections with confidence. Current forecasting systems can identify a large ejection after it has launched and estimate its arrival time and rough intensity. What they cannot yet reliably predict is the orientation of the magnetic field embedded in the cloud. That orientation, whether the field is northward or southward, pointing when it arrives, is one of the most critical factors in determining how severe the geomagnetic storm will be. And we typically do not measure it with confidence until the cloud is somewhere between 1 hour and 30 minutes from Earth, which is not much time to reconfigure a continental power grid. Research groups around the world are working on this problem. There are proposals for dedicated spacecraft positioned at points in the solar system that would allow earlier measurement of incoming cloud structure. There are improvements being made to the models that predict ejection trajectories and velocities. The data gathered from October 2024 is already being used to refine understanding of how sympathetic eruptions propagate and how preconditioning effects accelerate incoming clouds. The knowledge is advancing. The infrastructure hardening, however, is moving more slowly. The reason is familiar. It costs money now to prevent damage that might not occur for years or decades. Governments and utilities are not structured to respond well to that kind of calculus. The recommendations from space weather researchers have been on the table for more than a decade. Some have been implemented, many have not. There is another dimension to this that tends to get lost in the practical infrastructure discussion. The events of October 2024 reminded researchers of something fundamental about the relationship between Earth and the Sun that we have a tendency to forget in the ordinary business of daily life. We did not choose our location in the solar system. We orbit a star that is middle-aged and stable by cosmic standards, but stable is a relative term. On the scale of human civilization, a few decades long, the Sun appears calm and predictable. On the scale of centuries, it is not. It breathes in cycles. It rearranges its magnetic field every 11 years in a process so violent that the entire north and south magnetic poles of the Sun reverse. It throws material into space constantly and periodically, for reasons that are still not completely understood, it throws far more than usual. Earth's magnetic field is our shield. It has been protecting living things on this planet for billions of years, deflecting the constant stream of charged particles that the sun fires outward and channeling the energy from larger events into the harmless light show of the Aurora, rather than letting it reach the surface. Without the magnetosphere, our atmosphere would be slowly stripped away, as appears to have happened to Mars after its magnetic field weakened billions of years ago. But the magnetosphere is not infinite in its protective capacity. Large enough events compress it, distort it, force it to allow energy in through the poles, drive currents into the ground and through any conductive material in their path. The technology we have built on the surface of this planet is, in a sense, an extended nervous system running across the body of the Earth, and a large enough geomagnetic storm interacts with it in exactly the way you would not want. The story of October 2024 is therefore not just the story of an unusual event that disrupted some satellites and produced a beautiful light show. It is a data point in a longer conversation about the relationship between a technological civilization and the star that sustains it. It is evidence that the scenarios researchers have been describing for years are not hypothetical. The sun does, in fact, produce events of this magnitude. It aimed one directly at us and we survived it, partly through good management, partly through luck, and partly because the event, while record-breaking in its chain of causation, was not the maximum the sun is capable of producing. The question that October 2024 left hanging in the air was simple to state and difficult to answer. The next time the sun does something outside our observational baseline, will we be ready? The researchers who spent that week watching the data stream in, who made the phone calls and issued the alerts and watched the Aurora from their parking lots at 3 a.m, are not pessimistic people. Pessimists do not generally dedicate careers to watching the sun, but the honest ones will tell you that readiness is not the same as having survived the last event. It is a continuous process, and the process has not yet finished the work that October 2024 showed us still needs to be done. Our star is not an enemy. It is the reason anything on this planet exists. Every calorie of food ever eaten, every breath of oxygen ever drawn, every warm afternoon in the history of life on Earth came from that burning sphere 93 million miles away. It is generous in ways that are almost impossible to fully comprehend, and the energy it releases in its most violent moments is still only a tiny fraction of what it provides in the steady quiet of an ordinary day. But it is not tame. It has never been tame. We simply have not been paying close enough attention for long enough with good enough instruments to see it clearly. October 2024 was a moment when it reminded us of that. The sun is the most important object in the solar system, the foundation of everything we have and everything we are, and it can, without any particular malice or intention, produce events that would reshape the civilization we have spent 10,000 years building. We have the knowledge to prepare. We have the technology to detect and forecast and harden and protect. What we have been slow to develop is the collective will to treat this as the priority that the physics says it is. The sun is not done cycling. The maximum we are in will continue for another year or two before activity begins to decline, only to build again toward the next maximum a decade hence. The regions that produced October's events have rotated around the disk and will return. New regions will form. The magnetic pressure building inside the sun since the last cycle began to reverse will continue to seek release. The sky was full of colour that October night. Hundreds of millions of people looked up and felt something rare, the sense of being small in a very large and very active universe. For a few hours, the engineering alerts and the grid-switching decisions and the satellite anomaly reports were invisible. And what was visible was just light, the most ancient and original thing coming from 93 million miles away and painting the darkness above every continent on Earth. It was a warning dressed as a wonder. That is, perhaps, exactly what the sun has always been. What the October storm left behind was not just damage reports and insurance claims. It left a scientific community sitting with a data set that was, in some ways, more valuable than a clean miss would have been. A near miss that you can measure is worth more than a theoretical maximum you can only estimate. Researchers had, for the first time in the satellite era, a complex multi-stage solar event aimed almost directly at Earth, captured from dozens of instruments at multiple points in the solar system, with every stage of the storm's development recorded in detail. That data started changing things almost immediately. The first thing researchers began tearing apart was the preconditioning problem. The idea that earlier, smaller ejections could clear a path and allow a subsequent larger cloud to maintain its coherence was not entirely new. The theoretical framework existed, but seeing it operate at this scale, with this degree of measurable effect on the arriving cloud's velocity and structure, gave modelers something they had not had before, a real calibration event. You cannot tune a model without data that pushes it to its limits. October 2024 pushed the models to their limits. The results were humbling in some places and encouraging in others. The models that governed how fast the cloud would travel were the most seriously wrong. Several major forecasting centres had estimated arrival within a range that was off by several hours in the fast direction. That sounds minor until you think about a scenario where grid operators have been promised a window to complete protective switching, and the storm arrives before that window closes. Hours matter enormously in that context. But the models that predicted the geographic extent of geomagnetic disturbance were actually better than expected. The Aurora reaching into the subtropics was anticipated by the more aggressive forecast runs, and the areas that experienced significant grid stress largely overlapped with what the better models had flagged. That is progress. Not enough progress, not fast enough, but progress. The second thing that came out of October was a renewed and urgent conversation about something called the L5 mission concept. To explain why, you need to understand a little orbital geometry, and I promise it is worth it because this is one of those ideas that sounds esoteric and is actually critical. Earth orbits the Sun. Ahead of Earth in its orbit, at a point about 60 degrees out, and behind Earth in its orbit, at the equivalent position in the other direction, are positions in space called Lagrange points. The physics of gravity and orbital mechanics means that an object placed at these positions tends to stay there, orbiting the Sun at the same rate as Earth without drifting away. Space agencies have been using the L1 point, which is directly between Earth and the Sun about 1 million miles from Earth, for solar monitoring for decades. Spacecraft parked there have an uninterrupted view of the Sun and can give roughly 45 minutes to an hour of warning before an incoming cloud arrives. The L5 point is different. It sits behind and to the side of the Earth in its orbit. A spacecraft stationed there would see the Sun from a completely different angle, roughly 60 degrees around from Earth's perspective. That angle changes everything, because it means L5 can see the solar regions that are about to rotate into Earth-facing position days before they arrive. A large active region approaching from over the solar horizon would be visible from L5 for days, while it is still hidden from Earth and from the L1 spacecraft. Early warning becomes not hours but days. The European Space Agency proposed an L5 mission years before October 2024. It is in development, but the funding timelines and development schedules meant that when October arrived, no L5 spacecraft was in place. The farside region that produced the main eruption was detected through helioseismology, which is impressive science but which has limitations in both precision and response time that a direct-view spacecraft would not have had. In the months after the storm, the L5 mission concept became a different kind of conversation in research funding circles. It was no longer a blue-sky proposal competing with dozens of other worthy instruments. It was a documented need with a specific event attached to it. That kind of specificity changes how these arguments land in budget discussions, and by the middle of 2025, the mission's development schedule had accelerated in ways that would not have been politically achievable without October as a forcing event. There is something almost ironic about that. The storm was necessary to create the funding momentum to build the instrument that would have given us better warning of the storm. This is how infrastructure often works. The disaster creates the political will to prevent the next one. The problem with space weather is that the disasters are spaced far enough apart that the political will tends to erode between them. Researchers who lived through the period following major storms in the early 2000s can tell you exactly how that erosion felt. Watching recommendations gather dust as other priorities displaced them. Let me step back from the institutional politics for a moment, because there is a strand of the October story that gets less attention than the infrastructure discussion, and is, in some ways, more interesting to think about. We have been watching the Sun seriously, with proper instruments, for about 70 years. In that span, we have seen one full solar cycle, then another, accumulating slowly toward a picture of what our star does and how often. 70 years seems like a long time until you learn that the Sun's behaviour is influenced by cycles that operate on timescales of centuries and millennia. There are grand minima, periods of dramatically reduced solar activity that last decades. There are grand maxima. There are interactions between cycles of different lengths that modulate the overall pattern in ways that require centuries of data to even begin to identify. The last major period of extended low activity, a grand minimum that lasted from roughly the mid-17th century to the early 18th century, coincided with the coldest period of what historians call the Little Ice Age in Europe. The Thames froze reliably enough for frost fairs. The link between solar variability and Earth's climate on these longer timescales is a subject of genuine ongoing scientific discussion, not because the mechanism is mysterious in principle, but because the signal is small compared to other climate factors and extracting it cleanly from the historical record is genuinely difficult. What this means for the present conversation is that 70 years of careful solar observation, as valuable as that data is, represents a narrow slice of a much more complex pattern. The October 2024 event, which pushed or exceeded the limits of what the satellite era had documented, might not be an outlier relative to the full range of solar behaviour. It might be something closer to ordinary, observed during a monitoring period that happened to avoid the worst examples. Tree rings preserve a record of solar activity going back thousands of years. The cosmogenic isotopes deposited in trees and ice cores by high-energy solar particles can be read like a calendar, and the record they show includes events that dwarf anything in the instrumental era. In 874, a solar event left isotope signatures in tree rings that researchers have estimated at roughly twice the energy of the Carrington event. In 774 there was another, even larger. Scientists call these Miyake events after the researcher who first identified them in the tree ring record. We do not know exactly what physical process produces a Miyake-scale event. The leading hypothesis involves an unusually large and fast ejection, possibly combined with preceding preconditioning effects that sound disturbingly similar to what was observed in October 2024, only at a much larger scale. If a Miyake event hit Earth today, the isotope record suggests it would deliver somewhere between 10 and 20 times the particle flux of a Carrington event. The ground-induced current effects on power infrastructure would be proportionally larger. The space weather community discusses this scenario with the careful, calibrated tone that researchers adopt when they want to convey severity without inducing paralysis. But the underlying numbers are not something you can look at without sitting quietly for a moment afterward. The point is not to catastrophize. The point is that the monitoring era has given us an incomplete picture of what our sun is capable of, and that incompleteness has consequences for how we prioritize preparation. If you set your readiness thresholds based on what the last 70 years contained, you are implicitly assuming that 70 years is a representative sample. The tree ring record suggests it is not. This is an interesting problem in risk communication. How do you convey to a public, to a policy community, to a budget process, that the right comparison for space weather risk is not the largest event you can point to in living memory, but the largest event a proxy record suggests is physically possible? The answer is that you do it slowly, carefully, with a lot of peer review, and you accept that the message will not land as urgently as the physics might warrant, because human psychology is not built to respond to low-probability, high-consequence risks with the same urgency it applies to immediate vivid threats. October 2024 was the most vivid demonstration the space weather community has had in the modern era that these risks are real and present. Whether that demonstration translates into sustained action is a question that does not have an answer yet. Here is something else that October revealed, and this one is subtler and took longer to surface in the research literature. The storm's effects were not evenly distributed. This seems obvious when you first hear it, but the pattern of which systems were affected and which were not was not entirely what researchers had expected, and the reasons were genuinely illuminating. The parts of the power grid that experienced the most stress were not necessarily the oldest or the least maintained. They were, in many cases, the ones with the longest transmission lines running in directions aligned with the geomagnetic disturbance. Geomagnetically induced currents flow through long conductors, and a line running roughly north-south during a storm that is driving currents in the east-west direction will experience different stresses than an identical line running at a different angle. The geometry of a grid, the directions its major transmission corridors run, turns out to matter enormously. in ways that are not immediately intuitive and that are not always reflected in standard vulnerability assessments. Satellite operators, similarly, discovered that the correlation between a spacecraft's altitude, orbital inclination, and shielding design on one side, and its actual vulnerability during the storm on the other side, was messier than pre-storm models had suggested. Some satellites with older designs performed better than expected. Some newer ones, equipped with more sophisticated electronics that are by nature more sensitive to radiation, suffered more significant anomalies. The miniaturization trend in spacecraft design, which has democratized access to space and enabled the proliferation of small satellites for communications and Earth observation, has also produced a generation of spacecraft with components that are in some ways more vulnerable to radiation events than their larger predecessors. This is not a condemnation of small satellite technology. The capabilities it has enabled are genuinely transformative, but it adds a dimension to the space weather risk picture that was not fully appreciated before October, and the analysis that followed the storm has led to updated recommendations for how small satellite operators should plan for storm responses. The GPS issue is worth dwelling on separately, because it connects in ways that many people have not thought through to systems that seem completely unrelated to space weather. The degradation of GPS accuracy during the storm was, for most users, an inconvenience. If your car navigation routed you to the wrong entrance of a parking lot, that is annoying but not catastrophic. But GPS is not just a navigation tool. It is the global standard for precise timing. Financial trading systems use GPS timing to synchronize transactions across networks. Power grid management systems use it to coordinate switching operations across hundreds of miles. Telecommunications networks use it to maintain synchronization between base stations. Modern aviation approach systems use it for precision landing and reduced visibility. During the peak of the October storm, the timing accuracy available from GPS degraded by amounts that were measurable and significant for the most demanding applications. Backup systems engaged in some cases. In others, the degradation was absorbed as acceptable uncertainty. The post-storm analysis of which critical systems have robust GPS-independent timing backups and which do not has produced some uncomfortable answers. The answer for many systems is, the backup exists on paper, but it has not been tested at scale, and there are meaningful questions about how well it would actually perform if GPS became unavailable for an extended period. A Carrington-scale storm could take GPS satellites offline entirely, not just degrade their accuracy. The radiation environment in a very large event can saturate the sensors on navigation satellites to the point where they cannot reliably transmit usable signals. Timing-dependent infrastructure that assumes GPS availability as a baseline assumption would face a genuine crisis. This is one of those cascade failure scenarios that looks almost invisible until you start following the dependencies. Power grids use GPS timing. Financial systems use power and GPS timing. Communication networks use power and GPS timing. The dependencies stack in ways that mean a GPS disruption of sufficient magnitude and duration is not just a navigation problem, it propagates. Research groups studying infrastructure resilience have been pointing this out for years. The October storm provided a mild version of the demonstration. Mild enough that GPS did not actually fail, only degraded. Mild enough that the degradation was absorbed rather than causing secondary failures, but the researchers studying the event aftermath are clear that the mild version should not be taken as evidence that the severe version would be similarly manageable. There is a particular quality to these conversations, and I have been in several of them with people who spend their careers thinking about this, where you notice a gap between what the person being careful and professional will say on the record and what they will say when they are not thinking about how it will be received. The on-the-record version is measured, probabilistic, focused on the actions being taken and the progress being made. The other version is simpler. We are behind, not catastrophically behind. Not irretrievably behind, but genuinely, consequentially behind. The gap is not for want of knowledge. We know what needs to be done. We know it in detail. The hardening requirements for power transformers have been documented. The L5 mission exists as a fully specified design. The backup timing protocols are understood. The satellite shielding improvements are technically feasible. The space weather forecasting improvements are achievable with resources that are modest relative to the risk being mitigated. The gap is a political and economic problem dressed as a technical one, and October 2024 was an event that had just enough severity to get people's attention, and not quite enough severity to force the kind of urgent, sustained action that the research community believes the situation warrants. How many more close calls of that kind we get before one that tips over the threshold into genuine catastrophe is a question without a known answer. The Sun is not running a predictable schedule that we can read ahead of time. It is doing what it has always done, moving through its cycles, building and releasing magnetic stress, occasionally producing events that land at the extreme end of its output. Whether the next extreme event is a month away or a decade away is genuinely unknown, and everyone who tells you otherwise is overstating their confidence in the models. Let me take you somewhere specific, because the abstract risk landscape I have been describing becomes much more real when you put it in a particular place at a particular moment. In the spring of 1989, a solar storm hit Earth that was not as large as the Carrington event, but was large enough to matter. It struck on the 12th of March, and within 90 seconds of the storm's peak intensity reaching Quebec, Canada, the entire provincial power grid collapsed. Not some of it, all of it. 5.8 million people lost electricity simultaneously, and the outage lasted 9 hours. 9 hours. Not 9 days, not 9 months. 9 hours, and already the consequences were significant. Hospitals strained against their backup generators. The Montreal Metro shut down with passengers inside. Businesses across the province faced losses from interrupted operations. The economic cost was substantial. What researchers who studied that event carefully noted was not how bad the outcome was, but how close the outcome came to being much worse. Several transformers in the northeastern United States experienced damage that was not apparent until long after the storm, a kind of cumulative injury that reduced their remaining service life. Had the storm arrived slightly differently oriented, had a few more of those transformers failed outright instead of simply being degraded, the cascade could have spread south into the American Northeast. The Quebec event became, for a generation of power engineering researchers, the reference case for what a severe geomagnetic storm does to a modern grid. It was also, in a strange way, a kind of gift. The grid that existed in 1989 was simpler than the grid that exists today. It had fewer interconnections and fewer automated systems that could accelerate a cascade. The modern grid is more efficient and more capable, but more efficiency often means less redundancy, and less redundancy means a disturbance that would have been contained in an older, simpler system can propagate further in the current one. The engineers and managers who restored the Quebec grid in 1989 had something that engineers facing a severe 21st century geomagnetic storm might not have: spare transformers. Large high-voltage transformers are custom-built. They weigh several hundred tons. They take up to 2 years to manufacture, and there is a global supply chain bottleneck for them that is not resolved. The United States, as of the most recent assessments, has a strategic reserve of these transformers that would cover some replacement needs in a severe event, but falls considerably short of what a Carrington-level storm would require if the damage projections from research models are accurate. This is not a secret. The Department of Energy has published assessments, congressional hearings have been held, utility industry groups have discussed it. The bottleneck is not ignorance. It is the economics of manufacturing something that weighs 400 tons and might sit unused for 20 years. Nobody in the private sector is going to build a lot of those and warehouse them on speculation. The gap persists because the costs of closing it fall on the present, and the benefits accrue to a future event that might not come in anyone's current planning horizon. The October storm, interestingly, created a small but meaningful shift in this specific area. In the months following the storm, the pace of conversations between government agencies, utility operators, and domestic manufacturers about transformer reserve capacity visibly accelerated. Whether that acceleration translates into actually closing the gap rather than just mapping it more thoroughly is a question with a timeline measured in years rather than months. I want to shift direction slightly and talk about something that happened during the October storm that received almost no mainstream coverage, but that researchers found deeply significant. What happened at Mars? Earth is the only planet in our solar system with both a strong global magnetic field and a thick atmosphere, and the combination of those two things is what makes it habitable. Mars has neither. Its global magnetic field collapsed billions of years ago, leaving only scattered remnants in the crust. Its atmosphere is thin enough that the surface pressure is less than 1% of Earth's. What protects Mars from solar activity is essentially nothing. When the October ejection swept through the inner solar system, spacecraft orbiting Mars recorded the effects. The radiation environment around Mars during the storm peak was significantly elevated above background levels. Instruments designed to measure just this kind of environment, instruments placed there precisely because Mars is a destination for future human missions, recorded data that researchers are now using to refine their understanding of what a crew on or near Mars would face during a major event. The numbers are sobering in the way that precise numbers about radiation exposure tend to be. A crew on the Martian surface during a storm of that magnitude, without significant shielding, would receive a radiation dose that would push against or exceed career exposure limits established for astronauts. Not instantly fatal, not acutely incapacitating, but meaningful in a cumulative health risk sense. Repeated exposure across a multi-year surface mission would be a genuine concern. The good news is that Mars has options for shielding that are actually more available than they are in deep space. Subsurface habitats, lava tubes, berms of regolith piled against surface structures, even water walls in the right configuration can substantially reduce the radiation dose from a solar event. But these are design requirements, not afterthoughts. A surface habitat on Mars that does not account for solar storm shielding as a primary engineering constraint is not a serious design, and the October event contributed a calibration point to that engineering challenge that the mission planning community is actively incorporating. The deeper context here is that every significant solar event of the current cycle is, among other things, a data collection opportunity for the Mars mission planning that multiple agencies and private organizations are working toward. The constraints are real. The solutions are achievable. The data from events like October 2024 is what allows engineers to know how much shielding is enough rather than guessing. The same logic applies to lunar operations. The Moon has no magnetic field and only traces of the most tenuous possible atmosphere. Astronauts on the lunar surface during a large solar event would face a radiation environment substantially more hazardous than anything experienced by astronauts on the International Space Station, which sits inside Earth's magnetosphere and benefits from its protection. The Artemis program, which aims to return humans to the Moon, treats solar storm sheltering as a serious operational requirement, not an edge case. The events of October 2024 provided a direct operational test of the early warning infrastructure and response protocols that would protect astronauts in a lunar scenario, and the conclusion of that test was that the warning time was adequate for the current scenario, but would need to be longer for the faster or more severe scenarios that represent the upper end of the risk distribution. This conclusion landed in operational planning documents that are shaping the design of lunar habitats in ways that would not have happened with the same urgency without a real event to point to. There is a thread running through all of this. A single observation that keeps surfacing whenever you look carefully at how October 2024 changed things, and it is worth stating explicitly. The event was large enough to be useful but small enough to be survived. That sounds almost cynical, but it is not meant that way. It is an observation about the relationship between experience and preparation, about how institutions and systems actually change. A complete catastrophe would have forced change by necessity, but at enormous cost. An event that leaves no mark produces no institutional response. What lies between those extremes, an event severe enough to make the risks vivid and specific, but not so severe that the response is purely reactive, is the kind of event that actually moves preparation forward in a sustained way. The space weather research community did not choose October 2024. The Sun does not plan its output around human readiness schedules. But the particular combination of magnitude and timing and scientific documentation produced something genuinely useful, a forcing event that had real consequences but did not consume the resources and attention needed to respond to it with new preparation rather than just recovery. Whether we use it well is, as I have said, still an open question, but the inputs are there. Let me go in a different direction now, because the story of humanity and the Sun is not only a story of risk, it is also a story of how we learned, gradually and imperfectly, to see our own star. The history of solar observation is shorter than most people realize. For most of human history, the Sun was simply the source of light and warmth, studied as a theological object, a mathematical object for calendars and navigation, but not as a physical system that could be understood from the inside. The idea that the sun was a sphere of burning material similar in kind, if not in size, to earthly phenomena, rather than a divine lamp or a perfect celestial fire, took centuries to establish and involved intellectual battles that were more social than scientific. Galileo's telescopic observations of sunspots in the early 17th century were not just observations. They were a claim that the sun had blemishes, that the celestial sphere was not perfect, and that claim had implications that went beyond astronomy. The controversy around what the sunspots were, and whether they were actually on the sun's surface or were small bodies orbiting, it was resolved in favour of the surface interpretation, but it took time and required navigating a landscape of competing institutional interests that had nothing to do with the physics. By the mid-19th century, when Carrington made his observation, solar science had a foundation of systematic sunspot counting, emerging ideas about solar cycles and the beginnings of spectroscopy that would eventually allow researchers to determine the chemical composition of the sun's atmosphere from Earth. What Carrington lacked was any framework for understanding what a solar flare actually was. He knew he had seen something extraordinary. He had no way of knowing that what he witnessed was the release of energy equivalent to roughly 10 billion atomic bombs, travelling outward at a significant fraction of the speed of light. The framework that explains solar flares, coronal mass ejections, and the full machinery of space weather was assembled over the following century and a half through contributions from physics, magnetohydrodynamics, plasma physics, and eventually direct in situ measurement by spacecraft that could fly through the very phenomena they were studying. The word plasma, for instance, which I have been using throughout this script as though it needs no explanation, was not formalized as a description of a fourth state of matter, distinct from solid, liquid, and gas, until the 1920s. The behavior of magnetized plasma, which is what most of the interesting physics of solar activity involves, was being worked out theoretically in the mid-20th century at the same time that the first artificial satellites were being designed and launched. The gap between the science and the observational capability was so narrow that the first generation of space weather instruments was partly designed around theories that were still being worked out in the same years. This history matters because it establishes something important about where we currently sit in the development of solar science. We have had spacecraft watching the sun continuously for a few decades. We have a theory of solar magnetic field behavior that is well developed but not complete. We have global models of how solar eruptions propagate through interplanetary space that are regularly updated and improved. We have a community of hundreds of researchers actively working on every aspect of this problem, and we still cannot reliably predict the magnetic orientation of an incoming cloud until it is about an hour away. That specific failure is not for lack of effort or intelligence. It is because the physics of how the internal magnetic structure of an ejection evolves during its travel from the sun to Earth involves processes that are genuinely difficult to model. The cloud is not a rigid object with a fixed orientation. It rotates, it interacts with the solar wind, it gets deflected, it can merge with preceding ejections in complex ways. The orientation you measure at the sun is often not the orientation that arrives, and the orientation is what determines how hard the storm hits. Closing this specific gap is one of the clearest technical priorities in space weather research. The approaches being developed range from new theoretical frameworks for how ejection magnetic structure evolves, to machine learning models that look for statistical patterns between solar source region characteristics and eventual cloud orientation, to the L5 mission and similar proposals that would allow much earlier measurement of the cloud itself during its travel. Progress is being made. The October event added significantly to the dataset that all of these approaches are training on. But the timeline to reliable orientation prediction ahead of arrival is still measured in years to decades, not months, and the importance of that timeline should not be understated when discussing what it would mean to have truly adequate warning for the next large event. There is a peculiar human relationship to events that are both predictable in principle and unpredictable in specifics. We know earthquakes occur. We know roughly which regions are at highest risk. We cannot tell you that Tuesday at 3 in the afternoon is when the fault will move. Space weather is similar. We know large events occur. We know the current solar cycle is one of the more active in recent memory. We cannot tell you which month in the next 2 years will bring the storm that tests our preparation the hardest. The psychological response to this kind of risk profile is well documented in behavioral research. People are more motivated by concrete and immediate threats than by diffuse probabilistic ones, even when the probabilistic ones represent larger expected harm. The space weather community has been trying to bridge this gap in various ways, with varying success. One approach is the scenario exercise. Several governments, most prominently the United States and the United Kingdom, have conducted tabletop exercises and planning drills based on major space weather scenarios. These exercises bring together grid operators, telecommunications companies, government agencies, financial regulators, and others who would be affected by a severe event, and they walk through the sequence of decisions and communications that a real storm would require. The exercises have been valuable. They have identified gaps in communication protocols, clarified which agencies have authority to make which decisions, and in some cases led directly to changes in preparedness planning. The limitations of exercises are well understood too. They happen in conference rooms, not in real conditions, and the psychological reality of a major grid disruption or a prolonged GPS outage is not fully capturable in a planning session. The October storm, because it was real and happened in real time, provided a kind of learning that no tabletop exercise can fully replicate. System operators who made decisions in real time during that event know things about how their infrastructure actually behaves under solar storm conditions that they simply could not have known before. This is part of why the research community's response to the storm had an almost uncomfortable mix of scientific excitement and institutional relief. The excitement was about the data. The relief was about having a near miss that produced lessons without a catastrophe to recover from. There is a generation of space weather researchers whose entire professional lives have been oriented around communicating a risk that the public does not think about and that policymakers are slow to prioritize. October gave that community something they rarely get, a moment when everyone was paying attention. Millions of people photographing the Aurora, news organizations running stories about space weather for the first time in years, congressional offices asking for briefings, utility executives wanting to understand what had just happened to their grids. The window for turning that attention into durable action is not unlimited. Attention is always scarce and always competing with other claims on it. How effectively the research and policy community used that window in the months following October is one of the more consequential questions of this story. I want to spend some time on a character who does not usually appear in the space weather story, because understanding the full scope of what October 2024 meant requires thinking about someone who was nowhere near a telescope or a satellite operations center during the storm. Consider a farmer in Iowa. She runs a mid-sized operation that grows corn and soybeans across several thousand acres. She's not unusual. There are thousands of farms of this type across the American Midwest, and they represent a significant fraction of global food production. Her equipment in recent years has been increasingly guided by precision GPS. The planters, the combines, the sprayers all use satellite positioning to operate with accuracy that allows her to plant rows closer together, apply inputs more precisely, and harvest more efficiently than would be possible with the older methods. During the October storm, the GPS guidance on her equipment accumulated errors that made it unreliable for precision operations. The storm arrived during a period between planting and harvest, so the disruption was manageable. She switched to manual operations and accepted the inefficiency for a few days. The crop was fine. The disruption was absorbed. Now change one variable. Move the storm's arrival to a period of active harvest, when she and every other farmer in the region are operating around the clock in weather windows that may be only days wide. The economic analysis of GPS disruption during critical agricultural periods is something researchers have actually done, and the numbers are not trivial. Planting errors, inefficient inputs, harvest inefficiencies compounded across millions of acres and thousands of farms in a single growing season represent losses that aggregate into figures that would show up in food price indices. The point is not that this specific scenario is the most important consequence of space weather risk. It is that the dependencies run through the economy in directions that are not immediately obvious when you focus only on the most dramatic failure modes. GPS disruption is not just a problem for aviators and sailors. Precision agriculture is a GPS-dependent operation. Livestock tracking and management increasingly uses GPS. Supply chain logistics for time-sensitive goods depends on GPS-tracked shipping. The construction of buildings and infrastructure in the modern era involves GPS-based survey and layout tools. When space weather researchers talk about economic exposure to severe solar events, they are not just adding up the cost of damaged transformers and disrupted satellites. They are, or at least the most thorough analyses are, trying to capture the cascade through industries that do not normally think of themselves as space weather stakeholders. This is one of the more important communication challenges the field faces. The people who most need to understand the exposure are often not the people who attend space weather conferences or read journals about solar physics. They are supply chain managers and agricultural economists and hospital administrators and financial regulators. Reaching them requires translating the physics into the economic and operational terms that are legible in their professional contexts, and that translation work is harder and slower than the research itself. There are organisations working on this. National labs have published detailed economic impact assessments. Insurance industry groups have commissioned their own analyses. Some large financial institutions that are sensitive to infrastructure risk have begun incorporating space weather scenarios into their stress testing. These are real steps. They are not yet at the scale that the exposure warrants. The October storm moved this conversation a measurable increment forward. Sectors that had been abstractly aware of space weather as a category of risk became concretely aware of it as something that had just disrupted their operations in specific ways they could measure and document. That concreteness is valuable. Concrete operational experience changes how risk registers, and it changes how much internal advocacy for preparation is politically viable within organisations. I want to return to the sun itself for a moment, because there is something about what October revealed concerning the interior structure and behaviour of solar magnetic fields that I have been holding in reserve because it requires a bit of setup. The sun generates its magnetic field through a process called the dynamo. In the deep interior, where the outer convective zone meets the radiative zone below it, a region called the tachocline, there are enormous differential rotation rates. The outer layers of the sun do not all spin at the same speed. The equatorial regions rotate faster than the polar regions. This differential rotation twists and stretches the magnetic field lines that thread through the interior, and over the course of each solar cycle, the field lines become increasingly tangled, increasingly stressed, accumulating magnetic energy the way a twisted rubber band accumulates mechanical energy. Every 11 years or so, this accumulated stress becomes too great, and the field reorganizes. The complex tangled polarity structure from the previous cycle is replaced by a simpler configuration with reversed north and south poles, and then the process of accumulation and twisting begins again. The flares and ejections that reach Earth are the outward expression of this magnetic stress-finding release at the surface. What October 2024 suggested about the dynamo was subtle but important. The sympathetic eruptions across opposite hemispheres of the Sun, which surprised researchers by the distance they spanned, imply that the magnetic connectivity through the solar interior is more extensive than the models had captured. The standard picture of the dynamo, which is already mind-bendingly complex, may need revision to account for deeper or more diffuse coupling between different regions of the solar interior. This is not an abstract academic concern. If the interior coupling is stronger than previously modelled, then the chain reactions between surface regions during an active cycle might be more common and more powerful than the current eruption probability models predict. Not in a way that changes the overall risk picture dramatically, but in a way that shifts some of the probabilities at the high severity end of the distribution. And it is precisely the high severity end of the distribution that matters most for infrastructure planning. Helioseismologists are currently processing the October data with this question in mind. The technique involves extracting signals from the Sun's surface oscillations that carry information about the internal structure, essentially treating the Sun like a bell and reading what the reverberations tell you about what is inside. It is extraordinarily delicate work, requiring the kind of long baseline observations that only come from years of continuous monitoring. The answers will not arrive quickly, but they will arrive, and they will refine the picture of what the Sun is capable of and how often. The version of solar science that exists at the end of 2024 is more nuanced and more careful than the version that existed at the beginning of that year. That is how science works in practice. You build models based on available data. Events at the edges of the data challenge the models. The models are revised. The revised models make better predictions. The process is slow and rarely dramatic in real time, but looking back over years or decades, the cumulative change is significant. What October 2024 did to solar science is what a good stress test does to any complex model. It found the places where the predictions were weakest, documented the gaps, and provided the data needed to fill them. The science that comes out of this event will be better than the science that went into it. That is not consolation for the disruptions and the vulnerabilities that the storm exposed, but it is a real and important outcome. There is a kind of bittersweet quality to that, if you think about it a certain way. The progress in understanding comes partly from the vulnerability. The instruments get better, the models improve, the warnings become more precise, and each step in that direction is driven partly by an event that demonstrated the inadequacy of the previous step. The sun teaches by testing. Let me take you somewhere that most space weather discussions do not go, because I think it illuminates something important about the scale of what we are dealing with. The sun is approximately 4.5 billion years old. It formed from a collapsing cloud of gas and dust, ignited nuclear fusion in its core, and has been burning ever since. It will continue burning for approximately another 5 billion years before it expands into a red giant and eventually becomes a white dwarf. In the context of its full lifetime, the span of human civilization, even the span of multicellular life on Earth, is a fraction so small it essentially does not exist. During that 4.5 billion year history, the sun has been cycling. The 11-year cycle is well documented. There are longer cycles, a roughly century-long cycle of overall activity level that researchers call the secular cycle. And there are grand minima and maxima operating over timescales of centuries and millennia. Over its full lifetime, the sun has produced events across the full range of what its physics allows. Events like the one that left signatures in the tree rings of 874, events we have no proxy record for because they either did not hit Earth directly or occurred before trees or ice had accumulated in ways that preserve the record. What this means is that October 2024, as extraordinary as it was in the context of the 70-year instrumental record, is not necessarily extraordinary in the context of what the sun actually does over longer timescales. It may be close to ordinary for a high-activity period in a cycle that happens to overlap with the current phase of the secular cycle. The apparent exceptionalism of the event may say more about the brevity of our monitoring history than about the rarity of the event itself. This framing is not designed to minimize what happened. It is designed to calibrate our sense of where October sits in the full distribution of what we should prepare for. If the correct reference class for preparedness is the 70-year instrumental record, the preparedness bar is set in one place. If the correct reference class is the full physical range of what the sun produces, informed by the proxy records we have, the bar is set higher. The research community, in its internal discussions, tends toward the latter framing. The public communication tends to use the former, because the former is more defensible in terms of specific documented events, and avoids the communication challenge of explaining why a thing that is not in living memory is the appropriate basis for planning. Getting the framing right matters, not just for space weather, but for how we think about rare catastrophic risks in general. The Carrington event was outside the experience of everyone alive in its aftermath who had to rebuild the telegraph network. The Miyake-level events in the tree ring record were outside the experience of every civilization that has ever existed. But they were not outside the physical capability of the object that caused them, and that is the frame that should govern preparation. The October 2024 story has one more dimension that I want to give proper space to, because it is easy to get through the whole infrastructure and science narrative and miss the thing that is, in a certain light, most remarkable. Hundreds of millions of people experienced that storm. Most of them experienced it as light. For a few hours, as the Aurora burned across latitudes where it is almost never seen, something changed in the relationship between those people and the sky above them. It is easy to dismiss this as sentiment, as the soft part of a story that is mostly about infrastructure and risk assessment and orbital mechanics. But I do not think it should be dismissed, because the quality of the experience that night was not just beautiful. It was disorienting in a particular way that does not often occur in ordinary life. People who watched the Aurora from suburban lawns in the American South, who had never seen it before and may never see it again, were watching the direct visual result of a physical process 93 million miles away, arriving at their atmosphere at the same moment they were standing in their backyard. The light they were seeing was not a representation of that process. It was the process. The energized particles streaming down field lines and colliding with oxygen atoms overhead, releasing photons in the specific wavelengths of green and red and occasional purple, those photons then travelling from the upper atmosphere to the retinas of a person standing in a lawn chair in Tennessee. The whole chain complete and instantaneous in the way that light makes everything instantaneous. There is a word, sublime, that used to carry real weight before it got flattened by overuse. It originally described the experience of confronting something simultaneously beautiful and terrifying, something that revealed the scale of the world in a way that made the observer feel both very small and very much a part of something very large. The original formulation required both elements, not just beautiful, not just frightening, both at once, in a way that produced a distinctive and difficult-to-name emotional register. The Aurora of October 2024 was sublime in that original sense. It was beautiful, obviously, but it was also the visible surface of a process that, had it been 30 or 40% more energetic, or had the earlier ejections preconditioned the interplanetary medium slightly differently, would not have been a wonder. It would have been the first night of a crisis that engineers and economists and government agencies had been describing for years in papers that most people had never read. The people who photographed it from their lawns and shared those photographs by the millions were not wrong to see it as beautiful. The beauty was real. But the researchers who watched the same light from observatory parking lots and emergency operations centres, who understood what had been travelling toward Earth for the preceding 3 days and what the model said was in the range of what it could have done, those people were watching something different. They were watching the narrowness of the margin, and they were watching hundreds of millions of people see something wonderful and not understand what they were not seeing behind it. This gap, between the experience of the storm as spectacle and the reality of the storm as a near miss, is not a criticism of the people in the lawn chairs. It is a description of something fundamental about how technological civilization works. The systems that protect us from the hazards of living on an active planet have become so sophisticated and so embedded in the infrastructure that they are effectively invisible. When they work, you see nothing. When they almost fail to work, you see Aurora. The grid operators who spent those 18 hours making switching decisions that prevented cascades, the satellite operators who put assets into safe mode before the particle flux peaked, the aviation authorities who rerouted flights away from high-latitude disruptions, none of their work was visible to the people photographing the sky. The success of their preparation was expressed as something absent, as the crisis that did not happen, and absences are very hard to be grateful for because you cannot photograph them. We are as a species running on infrastructure that has become too complex to be fully understood by any single person and too critical to fail without consequences that most people have no framework for imagining. The power grid, the satellite constellation, the internet, the financial transaction layer, the supply chains, all of it has been assembled over decades by millions of people solving specific problems, and the result is a system that works extraordinarily well in ordinary conditions and whose vulnerabilities are only visible when something pushes it toward its edges. The sun pushes it toward its edges periodically, unpredictably, and with more severity than the 70-year monitoring record fully captures. October 2024 was such a push. It was handled. The next one, if it is larger, will require more to handle. Whether more is available when it is needed is a question whose answer is being written right now, in budget processes and engineering specifications and political decisions that most people do not follow and that do not generate the kind of dramatic imagery that fills social media feeds. The storm is not over in the sense that counts most. The October event itself ended within days, but the solar cycle that produced it continues. The gap between our readiness and the upper end of what the sun can produce continues. The work of closing that gap continues, imperfectly and not fast enough, but with a momentum that the October event pushed forward in ways that will take years to fully trace. What I find genuinely compelling about this story, having spent time in the research, is not the catastrophic potential. It is the human response to it. The people who have devoted careers to watching the sun, who have spent years publishing papers that do not make the news and attending conferences where the audience already knows the risks, who have given congressional testimony and written policy briefs and designed warning systems and advocated for infrastructure hardening. Those people woke up on October 4th to an event that was both a validation of everything they had been saying and a demonstration that more still needed to be done, and by and large they kept working. That is not nothing. The knowledge that a risk is real and serious and not adequately addressed, and yet continuing to work on addressing it requires a quality that is harder to maintain than alarm is. Alarm is easy. Sustained effort on a problem that the world is mostly not paying attention to requires something else, something closer to a particular kind of patience that comes from caring about an outcome without being able to control the timeline. The space weather research community has that quality in abundance. It has for decades. October 2024 gave them something rare, a moment when the world was paying attention. Whether that moment lengthens into sustained engagement or contracts back into the background is not something they control. It is something the rest of us have some say in. The sun will do what the sun does. It has been doing it for 4.5 billion years and will continue for 5 billion more. Our job, the particular and novel and historically unprecedented job of a civilization that has built itself into deep dependency on electricity and orbiting satellites and precision timing signals, is to understand our star well enough and prepare our infrastructure carefully enough that when it sends its next extraordinary message in our direction, we are ready to receive it without being broken by it. The aurora over Tennessee was real. The beauty was real. The narrowness of the margin was also real. All three things are true at once, and holding all three of them is not pessimism. It is accuracy. It is the closest we can come, sitting here on the surface of a small planet orbiting a middle-aged star in a quiet corner of an ordinary galaxy, to seeing our situation clearly. The sky was full of colour that October night because something 93 million miles away released more energy than all of human civilization has produced across the entire span of recorded history. And a fraction of that energy arrived at our doorstep in the form of light. It was a warning dressed as a wonder, as I said at the end of the first part of this story, and I do not think I can improve on that formulation, but I want to add something to it. It was also an invitation to look at the sky not just as a backdrop but as a surface, a boundary layer between the planet we live on and the vastly more energetic universe that surrounds it. An invitation to take seriously the systems that stand between that universe and the civilization we have built, not out of fear, but out of the same impulse that leads researchers to spend careers studying something most people have never thought about. Because it matters. Because the physics is real and the risks are real, and the solutions are achievable and the work is important. The sun is out there right now, cycling through the same magnetic process it has cycled through billions of times, building pressure, finding release, sending a constant stream of particles and light across 93 million miles of space. Occasionally, when the conditions are right and the magnetic stress has accumulated in the particular way it did in October 2024, sending something more, we are, for the first time in the history of life on this planet, a civilization capable of understanding what that means before it arrives. We built the instruments, we developed the theory, we created the warning systems. We have, imperfectly and incompletely but genuinely, begun to see our star clearly. What we do with that sight is up to us,